Hello everyone, my name is Hoang, and today I would like to present to you my research topic, which is microfluidic synthesis of graphene oxides manganese dioxide incorporated self-propelling micromotors for highly efficient organic dye removal. For the content of this presentation, we have four parts: introductions, experimental method, results, and conclusion. For introductions, dye pollution is a problem that is very relevant in our society. Dyes are utilized in various fields and indispensable in many of those. With their intricately designed structures to resist most type of stimuli, they pose many problems for the environment and the life of all beings. Thus, many methods has been developed to remove them from the environment to save the nature. One of the few noteworthy techniques that has been employed is dye absorption. Just by incorporating some adsorbent material into the dye-infected uh, wastewater, the dye molecule will be attracted and absorb onto the surface of the adsorbents, thus remove them from the water. However, this method has one key weakness, and that is the contact. It requires contact between the dye molecule and the absorbent material. Thus, that is one of the significant downside of this specific technique. Introducing micromotors, which is as its name call, micro size motor, which can be used to move in the aqueous environment through various different type of external stimuli. We have, for example, right here, magnetic driven micromotors. In the effect of magnetic field, the paddle on the micromotor will move and thus propel the micromotor in the water. On the right side, we have electric field-driven micromotors, which in this specific example looks like a windmill, and it moves under the effect of the electric field and thus propel itself in the environment. Next up, we have light-driven micromotors. So under the effect of light, a reaction can be occurred inside the designed micromotor, and propel it forward. And finally, bubble propel micromotor, which is which propel itself by formation of bubble, localized formation of bubble through a catalytic reaction. Most commonly is a hydrogen peroxide decomposition reaction. Now, all the micromotors we have proposed so far are pretty intricate and require scientific techniques to fabricate it. Thus, I would like to introduce you to the microfluidic technology, which is a technique that used to manipulate the flow of microfluid and create bubbles and vehicle to transport media inside of it. And the result are the droplets with multiple shell and core and are highly stable and monodispersed. And thus I propose uh, a system. And this is the schematic procedure of my sample. A capillary microfluidic system is employed to fabricate aqueous two-phase separated hydrogel micromotors with anisotropic shape for wastewater treatment. With the W1 here is deterrent solution, W2 is PGDA-GO manganese dioxide dispersion, and the O phase is dihexadecane and ABILEN90. And after the droplets were fabricated, the W1 and W2 phase will mix together since they are both aqueous, and after a while they will be separated due to the difference between their molecular weight, and then they'll be cured under UV light, and due to uh, uneven curing occur across the W2 shell of the micromotor, it pushed the W1 core uh, to the side, thus the name localized curing, and it will create a micromotors with concave dimple after finish curing and washing. The graphene oxide is employed here as a absorbent, owing to its 2D structure and plethora of functional groups on the surface. Manganese dioxide here is the catalyst for the hydrogen peroxide degradation process, which helps generate oxygen bubble, and it is the key for the bubble propelling property of the micromotors. Going to the results section, we first investigate the morphology of the micromotors, and the micromotor here has an anisotropic shape with a dimple on it. Now, the droplets were first collected and then cured, resulting in anisotropic shaped micromotor, and we then freeze dry them and observe them under SDM. And from there, two things can be pointed out. The outer surface of the micromotor is smooth. The concave dimple surface is much rougher. So the surface structure was caused by the migrations of dextrin in the interface of W1 and W2 into the droplets. Dextrin migrate from the W1 core onto the interface. And the rough surface facilitate bubble pinning, localize the bubble formation process, which is a key point for bubble propelling. Here is the video of a real-time movement of the micromotors. Now, after that, after we observe the motion, a few parameters have to be taken into consideration. An experiment was carrying out to figure out the optimal parameter. And after all this, the surfactant concentration of the simulated fluid was tested, and the optimal concentration is 0.01% weight. Hydrogen peroxide concentration is chosen as 2.5 weight percent, and a micromotor with 200 micrometer diameter with a concave dimple size of 86 micrometer. All this are the key parameters for the upcoming experiment, as they possess the best motion behavior, aka movement speed. Absorption performance analysis is next, and we tested with two types of organic dye, and for methylene blue, 34.07% removal capacity is for stagnant bead, meaning bead does not contain manganese dioxide, which is the catalyst. And for the micromotors, 84.91% removal capacity was observed, and this is for methylene blue. Same experiment was carried out with brilliant green, and same trend. 37.98% removal capacity for stagnant bead and 91.97% removal capacity for micromotors. And one key aspect of this system is their recyclability. So it has to be assessed. The micromotor will continuously used for 5 cycles of absorption without post-cycle treatment, and the absorption capacity decreased from 94.42% in the first cycle to 80.21% at the fifth cycle. So all in all, it's a 14.21% reduction after 5 cycles. So I concluded that this micromotor possess a high degree of recyclability. Thus, in conclusion, we proposed a simple, highly reproducible microfluidic method combining capillary microfluidics, aqueous two-phase separation, and UV-induced localized solidification to design and synthesize anisotropically shaped and propelling hydrogel micromotors capable of removing substantial quantity of contaminants in polluted water. The particle's morphology can be easily tuned by controlling the flow rate during the microfluidics process, and the swimming micromotors possess great dye absorption capacity and recyclability without the need for special treatment. This is the end of my presentation, and thank you for your attention.